Alright, so in this video we're going to cover power functions. Alright, so a power function is a function that takes on this form here, where we have, using our function notation. Alright, so it's one term. It consists of our variable x, some coefficient k, and some exponent p. Now, for it to be considered a power function, k and p can be any real numbers, right? So there's no restriction on the types. As long as they're part of the real numbers, then they can be whatever real numbers they are, and that'll still satisfy our power function definition. So that's a wide range of functions. We have some examples here of power functions are f of x equals 4x cubed, right? But based on this definition, we could have 1/3 x to the 2/3. But we can also have exponents that are fractions, right? And also, what falls into a power function are root functions, right? Because keep in mind that these roots are nothing more than rational exponents, right? And also some rational functions, right, where this is x to the -2. Right, so that'll also satisfy our definition of a power function. Right? And even the constant function. In this case, our k is 3, and our p happens to be 0, so x to the 0 is 1, so that leads us down to this power function here. Okay, so what we're going to focus on, at least in this chapter, is a very particular type of power function. So we're going to take a look at a power function where the exponent is a whole number. Okay, so we're going to look at whole number power functions that look like this. Okay, now in this case, k can still be any real number, right? And again, this notation, this like epsilon here, it's element of the real numbers. That's how you read that, right? So k can be any real numbers, but in this case, n is going to be limited to our whole numbers 1, 2, 3, 4, etc. Okay, so looking back at our power functions, that would disqualify these here for the types of functions that we'll be looking at. So we're only interested in something that looks like this. Even this, right? The whole number, I guess we could put in 0 there. So 0, 1, 2, 3, 4. Okay, so let's take a look at the graph and see if we can look at the behavior of some of these functions here. So what you see here is a graph of a power function, k x to the n, right? So k can be positive or negative, ranges from values. Here, just my graph just to see what these values do. Right? What I want to focus on here is, first of all, the change in the power. Right? So as n goes from 1 to 10, we can start to see here. As I kind of go through these powers, notice some similarities in some of these values and differences as well. So we could see here how these graphs change for each change in n. Right? Now, what if the k was also another change that's we want to take a look at is what happens when k is negative. Okay, so now we see how that affects our graph here. Okay, now what we're going to discuss first is this type of end behavior of the graph. Right, so by end behavior, I want to say, all right, what happens? We're here at our origin. How does the function behave as I move out towards negative infinity? And then here towards positive infinity. Now we can see there's really two general shapes here, right? This one, n is 2, which is our parabola function, which we covered earlier. And then our cubic, we see that these are the two general shapes here, right? As I get higher, it kind of flattens out near 0, right? But it has that same general behavior at the end, right? At either end, whether positive infinity or negative infinity. Right, so there's two cases to keep in mind here. One where our n is positive, our n is even, and our n is odd. And also when the k is positive or negative, we get a different behavior here. All right, you see the difference here. Okay, so let's kind of summarize this n behavior for even and odd power functions. Okay, so we have a summary here. Odd whole number power functions. Okay, so we're going to look at so we have 4 cases here. The first case is when k is bigger than 0, right? So we have a positive k. And when we have n is even, we have this general behavior where it does something like this, right? And when it is odd, we have this general behavior here. Now we want to look at what happens for the n behavior. Whole number summary. So here, n behavior. Okay, so I want to describe what happens as x goes to infinity, right? So I'm going to use this notation, right? X going towards infinity, right? And notice here the values of x, they keep getting larger and larger and larger, right? So as x goes to infinity, so does the value of the function. Goes to positive infinity. And the same thing for the odd powered function, right? As x goes to infinity, the values of the function also go to infinity. Now let's take a look at the other direction, right? So for values here to the left of the y-axis, right, the way we would write that is as x goes to negative infinity. Right, now in this case, the function values also are going, well, I shouldn't say also, the values here are getting larger and larger in the positive direction. All right, so f of x goes towards positive infinity as x goes to negative infinity. Now for odd functions, we have the opposite behavior. As x goes to negative infinity, these values continue to decrease. Right, they continue to decrease. So f of x in the negative direction, so they keep getting more and more negative. So the function goes to negative infinity. All right, so this is what we call the end behavior, right? So get comfortable with reading this notation right here. As x goes to infinity, the function also goes to infinity. As x goes to negative infinity, the function values go towards infinity for our even power. All right. Now, the second condition is we saw the behavior of the graph changed when this was negative. So we're looking at n behavior, and in this case when k is less than 0. Right, and in this case we saw that the graphs had this general shape here. Right, depending on whether n was even or whether n was odd. Okay, so let's try to determine here from the graph what happens as x goes to infinity. Right, so as x goes to positive infinity, we see values keep getting more and more negative. So f of x goes to negative infinity. Right? As x goes towards negative infinity, so going in the other direction, the values also go towards negative infinity. And it keeps getting more negative. So f of x goes to negative infinity. All right. Okay. Now for our odd numbered function values, here you see, okay, what happens as x goes towards infinity? And we can see from the graph, right, as x goes towards infinity, the function values keep getting more and more negative. So it continues to decrease in a negative direction. So we say the function values go towards negative infinity. All right, and then lastly here, as we go to negative infinity, the values in this case are getting larger and larger in the positive direction. So f of x goes towards infinity. All right, so let's keep the end behavior here in mind. Right, this is a good thing to kind of know, to kind of memorize and know offhand when we study our polynomials, which we'll introduce in a second. So what we'll see is that the leading terms in the polynomial will kind of take on this behavior of whatever the exponent of that leading term is going to be. Right? But before we get to that, let's formally introduce what we're going to spend the rest of this section covering, and that is a polynomial function. Okay, so a polynomial function So a polynomial function is a function that is a sum of power functions. So it has this general form, and I'll go over the notation in a second. All right. Okay, so you see the general pattern, right? The nth power, n minus 1 power, all the way till we get to the 0th power, right? We can write that as x to the 0, but that would just be 1, so we kind of just leave it off. Right? Notice that each one of these terms, right, we call this a term here. Each one of these is itself a power function. So we really have a sum of these power functions. Right? And in some cases, some of these coefficients may be 0. So if we have like something to the 3rd power, we don't necessarily need an x squared, an x, and a constant term. Some of those coefficients may be 0. So we do live the possibility that they're not 0. Okay, now a couple things here to just to define. As we stated, for it to be a polynomial, n must be an element of a whole number. Right, so 0, 1, 2, 3, etc. But for any of these a sub i's, I'll say, for I greater than or equal to 0, or less than or equal to n, any of those, what we call coefficients, is just some real number. Okay? All right. Okay. All right, so we'll take a look at some in the next video of properties of polynomial functions and how these properties affect the graph of these polynomial functions.